All right, thank you, Jim, and good morning to everyone. Thank you for joining us. My name is Mike Berg. I'm a business development manager in our industrial networks team for Panduit. I've been around at Panduit for a little while, for 30 years, believe it or not. So I've been in various different roles from R&D to product management, marketing, and now back in business development. I spent about 10 years as a product manager with our products that are for control panel builds. And I've had about 13 years in industrial networking experience. So I'm glad to be able to present with you today, or present to you today. The agenda, what we're going to cover, really what I'm going to cover here is really the structure. I'm going to try to provide you some information on the TIA 1005A, which is the applying Ethernet for industrial premises. I also want to give you some information on product selection and mitigation for environmental factors, especially that EMI noise, which is the topic of our webinar. And so then in the second half of our presentation, Jim Davis from Fluke Networks is going to carry on that conversation with regard to the standard. And he's going to be talking about testing, validating to that same TIA 1005A standard. So with that, I'm going to get moving here. All right, so why should you worry about the network physical layer? So sometimes we see that green light on the network switch, and the assumption is that we are good to go when we see that green light. And we assume that light means that we have Cat 5e or Cat 6a or gigabit performance when we need it. And our message to you today is to stop when you see that green light, don't go, and really evaluate, do you really have that level of performance? And so here's some factors to consider. So more than 50% of the failures in the network trace back to the data link and the physical layer. The potential downtime affects the OEE and can be costly for the end user. The manufacturers that are best in class OEE, those that have 90% or better OEE, spend more time on the data link reliability and physical layer. Second point here is that if we don't baseline the original cable installation, we don't know its capability when system growth and upgrades occur. And you need to recognize that in all likelihood, the hardware, the network hardware, the switches will turn over about 4 times over the life of the cabling. So the cabling will be in there 20 years or longer, right? And the network switch hardware turns over about every 4 to 5 years. So consider that in your planning. And then the third point being, as we're all seeing, network connected devices are rising, right? Along with the needs for real-time data. So nearly 60% of nodes now are on variants of Ethernet. So approaching the physical network layer with a disciplined approach can reduce the risks, and it improves our processes. So today's topic, what we're going to be talking to you today is about on the first half, giving you standards and giving guidance on installing the cabling infrastructure for reliability and availability, and especially when addressing that EMI noise factor. And the secondly, how you can better plan the system to baseline your testing and improve your knowledge of the system performance and ability to troubleshoot for reduced costs. So what I'm going to jump into here first is to try to give you some familiarity with these industrial Ethernet standards that relate to cabling and connectivity. So the Telecommunications Industry Association, or TIA, is who dictates these standards. And TIA is recognized across multiple premises by IT organizations in North America as a standard for network design and deployments, and they also apply in the industrial spaces. So if you're sitting in a commercial building today, or even residential as well, because there is a residential standard, your network is distributed following that commercial standard or that residential standard, and accordingly there are data center, healthcare, and industrial premises standards, all relating to how the cabling and connectivity gets distributed. So it really provides network as a discipline or as almost like a utility in these spaces. So these standards make the systems consistent, predictable, and easier to conduct moves, adds, and changes as time goes along, or to upgrade the system. TIA provides information you're probably familiar with, such as the 100-meter distance limitation on copper, 328 feet. It's part of the common standard, which is 568C. And it also, this standard also recognizes the component connector design and performance, things you may also be familiar with, Cat5e and Cat6 and Cat6a, and the fiber optic connectors. So all of these standards are recognized under TIA. And this includes now also the M12 connectors are recognized under TIA in the industrial standards. The TIA standards globally are harmonized with IEC and ISO. So there's a similar type platform globally for how systems are integrated. So to give you a little familiarity and set up on what the industrial standard is, TIA 1005A, this is the cabling and connectivity model. And conceptually, it starts at the bottom where it says EO, or equipment outlet. There are 2 and sometimes 3 sets of patching systems or distributors on the way up to the network core at the top. From the bottom up, these are depicted as distributor A, distributor B, and distributor C. Distributor C is the patching co-located with the actual network core equipment, and your distributor A would be your access layer switches. The cabling subsystems, the cabling connectivity, also start at the bottom and move up toward the network core. The links that connect the equipment outlet is called cabling subsystem 1, and then moving up you have subsystem 2 and subsystem 3 all the way up to the network core. So within the distributors are where the patching interconnects or cross connects occur. And this is, I'm telling you all about all this because this relates to the testing and how this actually happens and how you validate these systems. So it provides a testable and scalable plant floor cabling infrastructure. What you'll notice about this platform as well, you'll see 3-layer models, you'll see 2-layer models, and a single-layer model, right? So this shows the flexibility of the 1005 model, right? You can have home run, you can have multi-layer network structures within this model that correlate really well with how industrial networks are implemented. So let's relate now 1005A to those industrial networks and the Purdue model. So what you see here is an actual overlay of the Purdue model in the colors over that TIA 1005A model that I was showing you earlier. And here's some examples of how they correlate. So the structured cabling environment lives in conjunction with and is the connectivity system for the industrial compute platforms that might be at level 3, right, where your servers and storage and whatnot might be for your manufacturing plant floor. And then your intermediate distribution frames or your switches out on the plant floor that are helping control that copper run distance and providing you the right level of bandwidth and communications, those are at level 2. So your DB, where you see the boxes, and then your industrial switchers at the access layer deployed in control panels or are deployed in control panels or within zone enclosures. And those are at where you see that DA box or in your level 1 or level 0 environments. All right, so you might be saying to yourself, you know, this is great for a network engineer. So if I'm more of a controls engineer oriented person, why do I care, right? So here are some of the things that are really relevant, more so at that machinery level, equipment level, and control panel level. So some of the key differences or things that TI 1005A brings into play are recognizing the sealed connectors, the M12 D code, the M12 X code Ethernet connectors. So that's very helpful because these are common formats used in industrial, right? They're not really used too much elsewhere. The second thing is allowing multi-connector channels, those that would be a greater number of connectors than 4, right? Up to 6 connectors are allowed in the TIA 1005A standard. That's very important because we're talking about deploying equipment in control panels, and sometimes we need additional connectors to make sure that we're sealing that enclosure and that we can plug and play what goes into that panel. And then the third thing is this very important factor of what they call M.I.C.E, which M.I.C.E is really the environmental dynamics of the application. More so than any other premises, industrial has a wide variation on what happens environmentally. So this M.I.C.E rating is absolutely crucial with TIA 1005A. And what it is it's a standard to evaluate the space and then also evaluate what solutions, what products we're using in that space. So it looks at 4 factors: mechanical, ingress, chemical and climate, and electromagnetic. And then it also gives a rating scale there. You see M.I.C.E level 1, M.I.C.E level 2, M.I.C.E level 3. So the M.I.C.E level 3 would be your harshest environments. Your M.I.C.E level 1 would be something closer to what you would see in an office environment. And what that allows us to do is really rate that installation, design better considering the environmental factors, and select our product in a better way. Okay, so I want to pause here for a moment and also recognize, the whole world is not just about TIA. There are also global industrial Ethernet technology standards that we have to pay attention to and evaluate. So IEEE, Profinet, ODVA, Modbus, they're aligned with these TIA standards, but they also have specific requirements for using the components, connectors, and networks down at that machine level, control panels level, plant floor level. And they also address things like the real-time Ethernet requirements, right? So very important that we look at TIA, but also these global standards as well. So as we take the standards and we start to correlate them into the product solutions that are used out on the plant floor, what we can do is we can take that 1005A model, which we have in the background, and then we can build our solution based on that model, right? And we can also address those M.I.C.E factors. As we go down in this model, closer to the edge, the more the M.I.C.E factors come up, the more we need more industrial rated solutions. So we can build the solutions for the distributors, the A, B, and C, and provide the right structured cabling that goes along with that at the access layer, at the IDF layer, and then also at that core layer. And then we can also apply the correct cabling and connectivity solution, be it standard fiber or standard copper. And then as we get further down in the network, applying more of these sealed connectors. And so then we can also use the M.I.C.E factors to evaluate the space of where we're putting these products and where we really need to address those different M.I.C.E factors. So we can kind of do what they call M.I.C.E diagramming. We can take that overall plant view and say, okay, here are my hot spots, right? Something you would normally do in the design, kind of rate these different spaces and say, here's an area where I'd like to run my cabling because it's more of a M.I.C.E level 1. And then here's another area where I know I need sensors in this area, I can't avoid it, and so now I need a more harsh product in that installation. What it allows us to do is have a better design and control the costs so that we don't need, the harshest grade cable everywhere. We just need it where we have that M.I.C.E level 2 or M.I.C.E level 3. So what we do as Panduit to try to provide you some guides in this from this perspective is we actually go through and we rate all of the products we have in what we call a M.I.C.E guide. So we actually go through and rate all of the enclosure solutions as well as the cabling and connectivity solutions, and we give you a rating if it's M.I.C.E level 1, M.I.C.E level 2, M.I.C.E level 3. Now that's evaluating the environmental conditions. It's not necessarily that the product is built to that standard, but we can tell you, yes, it will fit well in this environment. So there's a nice guide that we're going to show you at the end for how you can use mice in practice. I want to give you a couple examples of mice. And so this is more so from the practical perspective and, routing, cabling, and pathways, which is a common thing to happen. So understanding the mice concept and how we can harden equipment as a way to address mice is one of the things to consider. So we can take our standard Ethernet cable up in the ceiling, we can put it in hangers. As we get a little closer down to the plant floor, maybe we're running it in trays. As we get right to where the machine level is, maybe we have it in conduit, right, for impact protection. And then as we get right to where all the action's happening, we may have sealed lay-in housings, or we may have pull-through housings that totally seal that enclosure and protect the cable and protect what's inside of that enclosure. So just some examples of how M.I.C.E is already applied today, right? And you can use that standard cable and you can use that pathway to kind of protect the cable. There's going to be other cases though where you're going to look and you're going to say, I'd rather have a hardened product to use. So in those cases, if you're more so at that distributor level C, where you're up at the core of the network, you're going to be using standard enterprise grade patch cords and standard NEMA 1 cabinets, right? But as you get further down into the network, maybe that distributor B level, or if you want to put your distributor C out on the plant floor, now you need something that's sealed, that's NEMA 12, that also addresses those mice factors, and your connectivity, you want that to be sealed from water spray, oil, dust, all these different factors, right? To give that reliability. So you can have that same performance level in the Ethernet cable, but you're just hardening the shell that goes around it. All right, so one of our biggest factors in considering mice, especially at the machine level and controls level, is dealing with EMI noise. And so this is an area that has a really big impact for design and product selection and just overall problems with troubleshooting that we have to deal with. So there's three areas I want to point you to in understanding this topic around EMI. And so from the Ethernet perspective, we're always going to want to look at the cable balance, how well designed that cable is in its symmetry, and we can evaluate that with testing. We also want to look at what are the sources of noise? Where is this noise coming from? And what types of noise do we have to deal with, right? It might be internal to the cable with the conductors, and it might also be external noise, high frequency noise that we're trying to drain off of that cable as well. So from a shielding perspective, we're dealing with trying to understand those noise sources and have a defense in depth strategy to help mitigate them. And then the final piece here that kind of makes it all work is the grounding and bonding system. And really in North America, we do not pay as much attention to the grounding and bonding system as we should, right? And probably for good reason, because a lot of the grounding and bonding systems in plants are a mess and they're hard to understand and they're hard to figure out how to attach to them, right? And so we come up with band-aids for how to deal with the noise issue. What I want to tell you about grounding and bonding though is consider the telecom grounding and bonding, the signal grounding and bonding in addition to your safety ground. And you can actually reference in 1005A some areas that are covered with grounding and bonding. So they cover the equipotential and mesh grounding systems and picking the right conductor sizing. They cover star grounding systems with an isolated ground, and they cover how to do the resistor capacitor termination and installation. All very helpful in understanding. In terms of the cable types, I mentioned cable balance. So a lot of times you're going to want to try to use unshielded twisted pairs, which is fine in a lot of spaces, right? And you can leverage that model to use UTP in that upper level of the installation very easily, right? But what we're telling you from a noise perspective is look at how well balanced and how well performing that cable is, even if it's not shielded, right? So have that well balanced cable and then figure out what types of noise you're dealing with and pick the appropriate cable. We're showing you different types of shielding that are available for the industrial cable types here. So it could be foiled, it could be shielded, it could be shielded, foiled, or screened, many different options available. You could have screening around the individual conductors or pairs, or you could have screening around that entire cable, or you could have both. And that more screened braid of a shield actually helps mitigate that high frequency noise that I was mentioning. So here's some examples as you're building out your shielding system within a control panel, or for the more of the machine level environment where you're installing components in a control panel. The cable's a big factor in it, right? Either your patch cord or your bulk cable, trying to make sure you've got the right amount of screening in it, that you've got the right amount of insulation on that cable as well, so it's electrically safe. And then teaming that cable with the right jack, field term plug, or M12 plug that can also be shielded, right? From an installation perspective, there are components out there that help ease the installation as well. So on the left-hand side, we're showing you a DIN rail patching solution that is shielded itself. What that will allow you to do is that data jack that you see right in the middle of the screen, or on the top middle, it snaps into that patch panel, and it establishes that bond to the grounding and bonding system right through the patch panel. So if you're putting 8 of those jacks in there, it simplifies that installation process. We also have shielded barrier products like the shielded wiring duct that we show here as well. If you're looking to give a little added protection to that cabling run, that Ethernet cabling run, from maybe some power cables that are nearby, the shielded wiring duct gives you that extra noise mitigation, that defense and depth that I was talking about. All right, so I'm going to come back to the TIA model here real quickly. So both point-to-point installations, cabling installations, and what we call the structured cabling are likely to occur on the plant floor. Using structured cabling in switch-to-switch connections is very appropriate and is recommended by the TIA 1005A, and is actually becoming more common on the plant floors. And we'll talk about why in a minute. Structured cabling to what is referred to as the horizontal connections or the downlinks is also recommended by 1005A. We're down at that EO level in the model. Extending structured cabling to this level provides greater testing capability when commissioning and troubleshooting the network at the edge of the network, or in cabling subsystem 1 in the TIA terms. In certain cases, such as in on-machine field connections, point-to-point cabling is the only option. And the test methods for point-to-point are different than with structured cabling using jacks. So different tests indicate the performance based on point-to-point or structured cabling. Okay, so I want to show you a little bit inside the control panel and how you can apply structured cabling. So the increased use of managed industrial network switches is making structured cabling a best practice in the controls cabinet. You can think of structured cabling as having a good plan for the field install connections that will mate up to the panel. In this regard, the patch panel in the cabinet is very much like a terminal strip or an interface module. In the diagram that you see here, you'll see structured cabling as a permanent link. That is the plant site cabling, and it has patch panels on either end, which are likely to be in a control panel or up a level in a data cabinet higher in the network. You're probably familiar that the overall channel length allowable for copper twisted pair is 100 meters. So together, the permanent link and the patch cord should not exceed this length to the TIA standard. And the permanent link cable is often solid core cable, whereas the patch cords are typically stranded cable. If you have long runs of stranded cable, you have to recognize that you'll derate that cable. You can't run that full 100 meters. So following this methodology simplifies the site work, and all the field connections will land in the patch panels. So it's a matter of patching those devices to the managed switch from that point. And here's a quick look at what that looks like in the field. This is a zone enclosure with access layer or distributor A level switches. So in a moment, we're going to turn the presentation over to Jim. And what we're showing you here, if you look at the diagram, the aqua colored, the thin cable in this image are the fiber backbone uplinks up to layer three, layer 3 switch in the IDF, and the green cabling that you kind of see in the background there, that's what we were referring to as the horizontal cabling or the downlinks that are connections to control panels or machines. So kind of my last area that I'm going to get into, I mentioned earlier 1005A and the multi-connector channels. So I wanted to give you a better feel as to where that would come up, right? So what I'm showing you here, here's that network zone enclosure that we saw on the previous slide, and here's kind of downstream from that network zone enclosure to some movable control panels where we might have an Ethernet connection. And in the middle there, you kind of see the diagram that we're building. On the left of the diagram is really the network zone enclosure. On the right of that little diagram in the middle is that movable control panel. And in between there, that little shaded area, that's where we have the harsh M.I.C.E conditions, which is a key factor to what we're looking at here. So inside those control panels, we can put our patch panels in. We can install jacks inside of there to allow the testing. And then we're going to have our rated, shielded patch cords inside those control panels as well. So that allows us to build out that network zone enclosure and that movable control panel and allow it to have connectivity between those two panels. Now, because this is a movable control panel and we've got a an elevated M.I.C.E level, we're going to put a bulkhead on that enclosure, right? So that's going to seal that connection, and it's also going to provide us a plug point, right? So now I can use a M.I.C.E rated cord set, something that's IP67, it might be shielded, and now I can connect between those two panels, and I can also move that panel around. So let's say this panel is used, sometimes it's used for a week, and then they pull it out and they put something else in, run a different line of production. That's what this multi-connector channel allows us to do. It allows a mobile panel and then also a sealed connection on either end. This is where you get into those situations where you get more than 4 connectors. So you might look at this and you say, well, that's a lot of different components to put into the system. There are ways to simplify this installation. So I'm showing you an example of that. You can take that whole jack patch cord connection and combine that into a single product. There are M12 small form factor solutions available that have that adapter built right into the cord set. So for that movable control panel, you can have that adapter on your enclosure wall and it goes right to that patch cord connection connecting up your PLC. So we're also looking at, how can we simplify the number of components in this system as well. So as I get ready to turn things over to Jim, I just want to show you real quickly, if you are testing and validating using the TIA 1005A model, you're going to be able to do that wherever you can define a channel or a permanent link, right? And so where I've circled there on the diagram, you may be doing 3 levels of testing at different levels of the network. You could do it at the machinery level, kind of downstream. You can do it from the IDF down to your access layer switches, and you can do it from the core of the network down as well. So capability to do this edge to edge testing, right? So my summary from the section here, review your internal standards for the network physical layer. Do they reference TIA 1005A, right? Use that 1005A and M.I.C.E concept to improve your designs and mitigate environmental factors. We're going to give you that guide to help you do that. And also learn and follow the control vendors' industrial Ethernet physical recommendations. They'll all tell you what type of media to use with the device or the switch. So in closing here, if you don't read TIA manuals, and you're never going to, reference controls guides out there that actually do reference the TIA model. So one of the controls documents out there is this deploying a resilient converged plant-wide Ethernet architecture guide. It's created by Cisco, Panduit, and Rockwell Automation. It covers logical network deployment and physical network deployment. So all these things I'm talking about, they're all in that guide, and it's written from the controls perspective. So if you're not really an IT person or know the IT standards, use this guide. The M.I.C.E selection guide is going to help you pick on product selection. Shielded cabling application guide is going to help you understand that cabling and grounding and bonding system. And all of the solutions I mentioned are in that smart control panel solutions brochure. All right, so with that, we're going to continue this conversation and bring in Jim Davis from Fluke Networks, and we are going to talk about testing to that TIA 1005A standard and really looking at that E factor and the MICE factors in your testing process. So with that, Jim, take it away.
Hey, good morning, everyone. Mike, that was really smooth. It almost looks like we practiced that transition. And by the way, I like how that presentation is maturing. I like that multi-connector slide. Very nice. So good morning, everyone. My name is Jim Davis. I'm a regional marketing engineer with Fluke Networks. I've worked with Fluke Networks for more than 20 years. Most of my time spent actually in South America, but I will try to avoid slipping into Spanish as we move forward today. This presentation really has two parts. The first part is an introduction to the basics of what we test to make sure that a cable is properly installed. I'm going to try and move through that a little bit quickly to spend more time on the second half to show how we test the cable to make sure that it will have all the possible noise immunity that is available for it. We always want to emphasize the importance of cabling working properly. There's some debate about whether cabling problems represent 20% or 50% or 80% of the problems on the network, but very often the cabling is going to be suspected of causing a problem in the network. Mike did a great job of reviewing these standards, but I do just want to draw attention again. We're very familiar with the 568 standard, the common standard. That is not only what guides the construction of the cables and the connectors, but that's also what is the guide for the people making the active equipment and the communications. They want to make sure that the electronic road, if you will, that's installed is going to support their new applications. Now, those of us in the data world are very familiar with the 568 commercial building standards. And I just want to emphasize again, this TIA 1005 standard is using the same types of components and it's to support the same applications, just for a more industrial environment. Now, in addition to the cabling standards, such as the 568, and there's an international version, the ISO 11801, these are very similar. Then we're going to find the application standards. And those application standards, again, are going to define the vehicles that travel on our electronic road. Let me step up on my soapbox here for a moment. Why is it that you should test cabling? I'm buying a perfectly good cable, really good jacks, and I have an installer who has a piece of paper that he actually participated in one of my presentations. That's great. It's a step in the right direction. But we want to make sure that the installed cabling works and delivers the performance that we're getting. It's a way to pay the people for the job. Before we close out the job, let's make sure we have those test results that the cabling is installed properly. Experience shows us that certified networks run faster, fewer errors. The cabling is going to be in the wall as long as 20 years. When you are installing a new machine, it can reduce the startup time. It's terrible. Build a machine, take it out to the site, find out the local network is not adequate to support it. And of course, if anything's down, let's get it back up. And finally, I throw out this caution. Beware of people who offer to save money by not certifying. This cable is so good, it doesn't need to be tested. If that cable was so good, show me, test it. It's not that we doubt, well, we doubt. So what is it that we're measuring? Basically, we're going to measure signal and noise. Provided we have more signal than noise, we're going to be able to have our communications. For a long time, we bypassed this basic one because we just assumed that everyone understood. This is actually a test result from a tester, and it's showing the cables on one end going to the other end. In this case, they're in order, they're passing. But this is where many of our problems are in the cabling, so I'm actually going to give a moment. Very often we talk about the registered jack, number 45. We have the jack on the left, the plug on the right. But in the industrial environment, we're also going to have these so-called M12 connectors. These come in two flavors, D for data, which has two pairs, and the new X, X for Roman numeral 10, or 10 gigabit, that actually has four pairs, so it can actually support network speeds up to 10 gigabits. Most common problems, somebody leaves a pair open, they invert a pair when they're installing it. There might be a short on one of the lines, especially those shielded cables, some of those uh, stranded wire shields. I'd hate to have a little piece of that wire fall in and make a short somewhere. There are two common wiring schemes, the A and the B. Neither one is better. The trick is to use the same one on both ends of the cable. The one cabling problem, the continuity problem that I want to draw your attention to is this split pair. Split pair is a really tricky one because you see conductor 5 goes to conductor 5 and conductor 7 goes to conductor 7. So with a simple continuity test, this looks like it's performing well. However, the cable is no longer in a pair, and it's the magic of the pair. It was actually invented by Alexander Graham Bell. The magic of the pair that allows the cable to resist external interference. So split pair is a little bit of a tricky one. We find that through a near-end crosstalk test. Now, let's take a brief look. And again, I want to spend more time on our measurements of immunity, if you will, to EMI. But to understand that, got to start with the basics. The first thing we're going to measure is the strength of the signal that we're transmitting. Actually, the loss of signal, but consider it the strength. So we're going to send a given signal down a wire. It starts with a given amplitude, and at the far end, a lower amplitude of the signal. Here we're looking again on the tester, the strength of the signal in decibels on the vertical scale versus the frequency. We're going up to 250 megahertz here. So this would be a category 6 test. This red line here is the limit for the standard. Sometimes, sticking to my road analogy, I like to think of that as the minimum height of an overpass. I want to make sure on this road, all of the overpasses have enough room for my vehicle. Now, one of the challenges is that as the cable gets longer, here's the measured value of a shorter cable, but as it gets longer, we're going to have more insertion loss. As with higher frequencies, we have more insertion loss. And something to be careful with, Mike mentioned this, in your industrial environments, when you get to a higher temperature environment, causes more resistance in the cable, and you may have to derate or reduce the length of your cabling to make sure you get adequate signal on the far end. Return loss, again, this is an internal noise to the cable, not an external noise. This is an internal noise, and it is a signal that gets reflected back to us. In gigabit Ethernet, we communicate in full duplex. We transmit and receive on the same pair. So if a signal is reflected back to us, that reflected signal is noise. We'd like to avoid that. Now, this can be caused by damaged cable. I can see sometimes in test results where somebody starts to work the cabling through the modular furniture, and you can see the breakdown in the cable. Separating the pairs changes the impedance and can cause additional return loss. And this final one, and curiously, I had a case yesterday where a customer said, "Why is my cable failing? I'm getting this strange image along the cable." And it was the return loss values coupled together like this, which means, unfortunately, they have water in their conduit. Now, I want to bring up an important point here, and that is about the types of components that we're using. We want to use components that are rated for the environment we're using, and we can't go back after the fact and say, "Oh, I want to have a cable, I'm planning to run 10 gigabits, so test that cable to category 6A. Did you install category 6A cable? Because if you installed category 5E and now you want to run 10 gigabits, it's not going to work. It's not that the cable is bad, it's the wrong cable for that application. As was the case in this situation, they used an indoor rated cable in an outdoor environment and it failed. One last noise parameter, and again, this is an internal noise parameter to the cable, is something we call near-end crosstalk. In the olden days, you had a telephone in your house. Sometimes when you would pick up that telephone, you could hear your neighbors talking on the line. That was the crosstalk. Same thing under the jacket, those 4 pairs, we can get a signal that bleeds, if you will, is induced from one of the pairs over to the adjacent pair. If we measure it on the near end, it'd be near end crosstalk. On the far end, that would be far end crosstalk. Now, one of the things that is most likely to cause near end crosstalk is actually the construction of the RJ45 connector. I really appreciate the RJ45. Runs 10 gigabits. That's quite a bit of performance. the backwards compatibility, the interoperability of it. I can plug a category 5E plug into a category 6A jack and get 5E performance just fine. If you've ever traveled, I've had the experience of going from England to France to Germany. I need 3 different adapter plugs for my outlet so I can plug in my cell phone to charge it, but my data cable is exactly the same all over the world. Next can be caused by a damaged cable or a poorly made cable, not maintaining the twist. Again, that twist is very significant in keeping the signal in there. And again, the wrong category of cable. So if we put these 2 measurements together, the signal strength and the noise level, that'll give us a signal to noise ratio. And the better the signal to noise ratio, the faster we can communicate. Real quickly, what we're looking at here is the limit line, the height of the bridge, if you will, the minimum height of the bridge for category 5E. And we see that this goes out to 100 megahertz. I'm going to leave my cursor right here at about 58 dB to show the difference between category 5E and category 6. So category 6, the line is a little bit higher, a little bit tighter, and it goes out to 250 megahertz. Now, category 5E can run really fast. Gigabit Ethernet, absolutely all day long, should run on 5E. And they've even come out with some new velocities, 2.5 and even 5 gigabit Ethernet that is supposed to run on category 5E cables. A lot of times I'll see customers installing category 6 cables because, well, I don't want to be minimally compliant. The cost of the cables is similar. The cost of the installation is the same. Cost of it replacing it is difficult. Now, for very high speed connections, I have customers who are doing optical applications. They have a camera on the end of a robot. The robot needs to transmit a high definition image. They may step up to category 6A, which can support 10 gigabit Ethernet transmissions out to 100 meters. Another day we'll talk about category 8. Category 8 only goes to 30 meters. So most often what we're seeing is category 6A, the top of the line. Now, before we jump into our immunity and the way we measure immunity to external noise, this might be the 2 most important slides in the presentation, and it actually has my part of the presentation. It has not so much to do with the measurements, but I want you to be comfortable reading a test report. Another day, another presentation, we'll talk about NVP and propagation delay and these numbers and graphs. But if somebody is giving you a test report, I want you to have confidence to be able to read that. And this is the test report that comes off of our tester. And the 2 fields I want you to look at, first is, did the test result pass? It seems silly, it seems obvious when you're looking at a passing test result, but make sure it passes. And the second field that's very important, what is the test limit? What was the requirement of the height of the overpasses that was being used? In this case, they've tested against category 6 permanent link limits. Now, if you were asking for category 6A, this doesn't confirm that you have category 6A, just category 6. So again, did it pass? What test limit? All right, all that stuff is great, but what about my difficult environment? I've got 100 horsepower motors and VFDs and transformers. I have an arc furnace here. What am I going to do about all that noise? Well, I just want to touch real quickly on the M.I.C.E classifications. An important thing in the 1005 standard is it spells out what is the rating, what are the mechanical requirements of a M.I.C.E 1 versus a M.I.C.E 2 versus an M3 environment. Same with ingress. Now, this mechanical ingress and the climactic or chemical, I'm going to pass all of that over to Panduit. That's physical requirements. That's the jacketing of the cable, perhaps even an armored cable. Will that cable be resistant to water? Will that cable be resistant to soaking in oil? What I can help with is the testing around the electromagnetic interference. And the 1005 has specific definitions of the noise levels that represent an E1, an E2, or an E3 environment. Running tests to determine if you have an E1, an E2, or an E3 environment can be challenging because you kind of need to test everywhere all the time. One point I want to throw out: if you are using managed switches, the managed switches through the Simple Network Management Protocol, SNMP, can report to you if they're finding physical layer errors on the cabling. So that managed switch, in a way, can serve as a measurement of noise everywhere that your cable is running. I'm sorry, it's a little bit too late if you're starting to find a lot of physical layer errors through the management port, but seeing those physical layer errors can suggest that you are in an electronically noisy environment. Now, our big concern with the noise is that we're going to get corrupted frames. On the physical layer, we're going to get cyclical redundancy check or frame checksum errors. You may not realize that these FCS errors or CRC errors are even happening because Ethernet's pretty reliable. And if a frame doesn't get there, it's going to retransmit it. The problem is there's a delay while we're waiting for the retransmission. And if something really important needs to happen during that delay, like you need to shut the line down, that can cause a problem. So technically, the specification of a CRC error is this, it's caused by the checksum generated by the transmitting device not matching the one generated by the receiving device. So let's drill into this a little bit more to understand how they're generated. Oh no, protocol analysis. Ah, yes, it's too early in the morning for protocol analysis. I'm sorry if you really like protocol analysis, you'll be casting stones at me. But this is actually what an Ethernet frame looks like. This is coming from a protocol analyzer, something like Wireshark software, and it's showing the bits and bytes that are transmitted down the wire. So I want to just simplify this. At the start, at the front of our Ethernet frame, we have the destination address, where the frame's going. It's followed by the source address, where it came from. There's some protocol information. Are we speaking English or Spanish or HTTP or HTTPS? There's the actual cargo in the frame, what we're sending. And on the end, we have the cyclical redundancy check or frame checksum that makes sure that the sequence of bits and bytes were sent in the right order. So here, I'm going to send from my switch to my PLC through this cable a very simple communication: on, off, 1010. And I send 1010 down the line and I receive 1010, on, off. So my cyclical redundancy check matches up, the frame is received, and we move on. Now I'm going to transmit that same thing one more time, but just as I do, the VFD kicks in. We get a little spike of common mode noise on the wire, and what had been on, off becomes on, off. And the CRCs don't match up. And at the physical layer, we say this frame is defective, and we toss it into the bit bucket. Bit bucket is a technical term. You have to make sure to empty your bit bucket every day. So how can we avoid this noise? As Mike was mentioning, shielded cabling. And sometimes it's religion for people. We're going to use shielded cabling because there might be noise, and we're doing shielded because that's what the head office does. Great. As Mike mentioned, this is a complex subject, and we're not going to address whether you should shield or should not shield. But if you are going to shield and you have continuity of the shield from end to end, make sure that the shield follows the path of the cable. Older cable testers could be tricked. The way that we measured if there was continuity on the shield was to look for a low resistance path between the two shield conductors. Well, we found in certain environments, the two ends of the cabling may share a ground, or they may share a common conductive cabling path. If you're using a metal tray to support the cables that's conductive, and it would trick the cable tester into thinking that there was continuity in the shield. So the current revision of the standard specifically states that the shield needs to follow the path of the cable, and we run this test. What I'm showing here, I know you're not going to have two ends of the cable right next to each other, but here there's clearly a conductive path between the shield conductors on these two jacks. But we can see that one of these shields was not properly terminated. So if you're installing shielding, make sure it, it goes from one end to the other. Now, the other part, and here's a little bit of the trickier and a little bit deeper part of the presentation, is the importance of balanced cabling. So how does UTP even work? When I talk to the shielded department, oh my gosh, everything has to be shielded. If it wasn't shielded, there's no hope for it. Well, it works in the following way. When we're going to transmit a signal down our pair of cable, suppose the signal I want to send is plus 2 volts. So I'm going to send on one leg plus 1 volt and on the second leg minus 1 volt, giving me a difference of 2 volts. Now, as the signal travels down the cable, if each leg of the pair has the same electrical characteristics, has good geometry, we say that the cable is well balanced. So here's that noise spike, and as the noise gets on the cable, I'm going to say that we're getting a half volt that attaches to each leg of the pair. If we treat that half volt of interference the same way, then here we do go with some math. First thing in the morning, plus 1, plus a half, 1.5 volts, minus 1, plus a half, minus a half volt. We have maintained that 2 volt differential signal, and our communication just flies. Now, if the cable is not well balanced, as in this bottom example, we're not able to maintain the half volt of differential signal, and this generates our errored frame. Here's a quick look at this on an oscilloscope, and we see the noise on top of the square pulses that are being transmitted. So what is the way that we measure the balance of the cable? There actually is a test for this, and it's called transverse conversion loss, TCL. And specifically what we're going to do with TCL is transmit a differential mode signal into the cable, and we're going to measure common mode noise that is reflected back to us. So this is going to tell us how well the link that we have constructed avoids the conversion of differential mode noise into common mode noise. Now, this test is actually an inverse. You can also send common mode noise and measure differential coming back, test called LCL. That's for another day. So this is showing the ability of our link. Let's not get too hung up on the measurement of TCL, but that this is a measurement, if you will, of the immunity, the capability of our pair to avoid the external influence of the noise. So this table, we produce a chart, and in that chart, we take all the test limits that are in the tester. And I'm using this to explain the test limits for a category 6 test. Now, in the basic 1005 test, there is not a requirement, it's not mandatory to do TCL testing in the field. TCL has existed for a long time, but in the past, older cable testers weren't able to test TCL in the field. Modern cable testers can test TCL in the field. And so we see that on this minimally requirement test, there is no requirement for TCL. Here are the requirements across the frequency range for insertion loss, next, and return loss. So what we've done in the tester is we've added extended limits. These extended limits are named plus all. You'll see these are the values for an E1 environment. And these TCL values are specified in the 1005 standard. 1005 standard, and appreciate the standard is not me, is not Fluke Networks, it's not M.I.C.E, it's not Panduit. It's the knowledge of the market. It's many players in the market coming together and saying, if you have this level of TCL, you're going to be able to operate in an environment with this noise. So we're using those values specified in the standard, applying them to a field test, and we're going to measure both TCL and TCL on the far end, which is ELTCTL. Now, in a moment, I'm going to jump over to a slide where we're going to compare the values for TCL between an E1 and E2 and an E3 environment. But I wanted to point out here that the values for insertion loss, next, and return loss, here are attenuation to crosstalk ratios, but insertion loss, next, and return loss are all the same in an E1, an E2, and an E3 environment. The difference between the different links is based on the TCL values. So here is a graph showing in decibels across the frequency range, the values for the height of the overpass, if you will, the TCL for an E1 test. And here we're looking at an E2 environment, and we see that the line is higher up, the limits are tighter, and that tighter limit represents better noise immunity. And the E3 environment is even stricter, is even tighter. All right, so this sounds very interesting. I wasn't aware TCL can help me to make sure my cabling is going to have immunity to the noise environment, my environment. What should I specify? What should I tell people to test? Well, check with your consultant, the architect, the engineer who's designing the system. They're going to take into account what is the performance of the components you're using, what applications you're planning to support. I have a really low speed application. I've got a fan on the roof and I've got a sensor that tells me if the fan is on or the fan is off. That's pretty low speed data compared to the camera on the end of the robot. This is the M.I.C.E rating of the environment. Now, there is actually a cabling specification on our webpage, and it's Division 27, the whole 9 yards, 10 pages long. But I find that in the real world, I'm lucky if I get one cell of an Excel spreadsheet for the specification for the cabling. So we want to say there that the links shall be tested to the ANSI TI 568.2 is the copper version. We're on the D revision limits for the category that we've decided on. The specific test limit, the category 5E, E1 plus all limit is a good starting point. We can go up from there. We can go up to category 6. We can go up to an E2 environment as needed. Remember, this is coming from the 1005, which is part of the 568 specification. So, summarizing, get a good startup and minimize our downtime. Certify our cabling when we first install it to make sure it's properly installed. Check what limit is used on your test report. Here's a test limit, category 6A to the E2 limits. Ask for those TCL measurements. Asking for the plus all limits will make sure we have the noise immunity we're looking for. Use the right tools to do that. Again, my name is Jim Davis, and really I'm honored to be invited by Panduit to speak with you today. I thank you for the opportunity to reach out to you. And I also want to thank Brent and Jim, who took the initiative and said, hey, I want to talk to the customers in our area and offer them a better explanation of how we can keep their networks working. And with that, let me wrap up and see if we have any questions out there. If you have any questions, please send them in through the chat window. We'd be happy to talk through them with you.
Thank you, Jim and Mike. We do have time now to answer some questions, so please make sure to put them either in the chat box or the questions section of the GoToWebinar app. We have a few questions that came in while you guys were talking. I'm going to start with the first one. Is TCL testing required in the standards? I think that one maybe is directed to you.
I'll jump on that. Mike would be able to answer it as well. There are two sides, two ways to look at the standard. There are the component specifications, and the component specifications will tell us in the factory how they're going to be testing that cabling. and testing in the factory when they're designing the cabling, how it should work. And then there's another standard. Mike mentioned it. I should have brought it up more. The TIA 1152 standard, now in the A revision. And that talks about what tests we're going to run in the field and how we're going to run them and the accuracy. Within the 1152 standard, the values for TCL are specified, but it is not a requirement of the field testing. So yes, the standard specifies what the values are for TCL, but it's not mandatory to run the TCL tests.
Thanks, Jim. Our next question is, what is the difference between M12 X code and D code?
Yeah, I can take that, Jane. So the difference between the D code and the X code, they're both Ethernet cables and they're both use Ethernet connectors. The D code has been around for a lot longer time frame, and it has a different number of pairs. So it's got 2-pair cable and 4 conductors, right? And so it also has Category 5E performance, and it's associated with using the cabling for a smart block type application or a smart IO application. So the decode M12 is used for that purpose. When you get into processor-based equipment, switches and other devices that are going to run standard Ethernet, all 4 pairs, 8 pins, that's where you get into the X code. And Jim showed that diagram with the X that you can actually see on the front of the connector. So as you get into processor-based equipment, that's where you're going to see X code. D code's been out a lot longer. X code is newer, right, with the process-based and edge IoT type devices.
Okay, thank you, Mike. Our next question here, can I test TCL with my older DXT tester?
Let me run with that one real quick. Tried to mention, unfortunately, in the past, older testers were not able to run the TCL tests. So unfortunately, in the DTX or even the DSP 4000, the DSP 2000 series testers, there wasn't an option for TCL testing. That's a feature in our newer DSX 5000 or DSX 8000 testers. Thanks for that question, Jane.
Sure, looks like we have a few more that have come in here. You mentioned solid conductor Ethernet cabling. What are the advantages in using it?
So Jane, I can take that. So with the solid conductor cable, you're going to get the a better performance and a better reach or a better length reach in running that cable. So for a permanent installation, it makes sense to use the solid core so that the cable's not stranded on the inside. It fits with a permanent part of the installation. So when we were showing the jacks earlier, it would be the cable that would run to those jacks in a permanent installation. Where you have your patching, and sometimes you'll have patch cords, then you need that flexibility in the cable. And that's where it makes the most sense to go to a stranded cable. You're going to have to derate that cable for performance, but you also need that flexibility, right? You can't have a fishing rod out there in your cable, right? So it's a functional evaluation in using it in the patching applications or the point-to-point connections. So if it's a permanent installation, it's always a good idea to go solid core.
Okay, thanks, Mike. I think this next question is for you also. Are there differences between a standard STP cable and an industrial rated STP cable?
So that's a really good question, right? They're both going to be shielded cables, right? Because you can get something designed for a commercial space that would also be shielded, which it's probably going to provide you the good cable balance that we both talked about. It's going to provide you some noise shielding as well. What the difference is between that commercial grade and the industrial grade is in a few different areas, right? So the industrial cables, you can probably get an industrial jacketed version that's very similar to an office grade that has the same type of shielding. But when you start to consider multiple sources of noise, maybe, you know, in a commercial setting, we're most concerned about power and data being next to one another, but in the industrial environment, we're concerned about that, but then we're also concerned about RF noise and high frequency noise also occurring, right? So the industrial cable may have additional layers of shielding on it, which you've seen, right? And we covered some of that, or that that braided version of shield added to that cable design. And then it's going to have the more durable jacket and a higher insulation voltage rating on it, so you can use it and be electrically safe within the cabinet. So those are the big differences there. The commercial grade that's shielded has applications in industrial, but as you get more into those MICE factors, you're probably going to want to look at industrial rated cables.
Okay, looks like we just had a few more questions come in. The question came up actually a couple times here if we'll be able to send the PDF copy of this PowerPoint, and we will be sending a copy of it. It will be in your follow-up email that's sent with the video recording. The next question here that just popped up is, can you upgrade to Category 6A with existing Cat 5 without replacing and installing Cat 6A?
Can you repeat that one again?
You can certainly test your installed cable to a higher performance level. The measured insertion loss in the cable is what it is, and we can compare it against different limit lines. I have not seen cases where Category 5E cable is going to pass Category 6A performance, especially when we get into longer lengths. So I think that would be very difficult to see. If you have a shorter Category 6 link, could that support 10 gigabits? Yeah, it might support 10 gigabits. There's an expectation that it'll run out to about 50 meters, but running 10 gigabits on Category 5E cable would be a challenge.
Okay, thanks, Jim. Few more questions here. What should I be looking for to know the contractor is installing cabling to the standard?
So probably one of the first things is, you know, what have they agreed to do in terms of validation, right? So the test report that Jim was showing, do you have a specification, and then have they provided evidence that they've validated? That would be one of the best things to look at or to require. And from there, you could actually look at some of the other areas of the standard in terms of things like bend radius control. Are they controlling distances? Key elements of the TIA standards that you could look and see, are they doing these things? That takes a little more expertise and a walkthrough to be able to do it. So the test report is really the key primary thing.
Yeah, and complementing that, you might also look at the contractor and what their experience is. Do they have any, are they aligned with any manufacturer? Has Panduit authorized them to be an installer? Do they have a trained design person? Do they have trained technicians who have done this work before? Sometimes we come across the situation where we have electricians who are doing the installation work. No offense for a second to electricians, but the termination process is a little bit different, and that's the experience. There are electricians who have a lot of experience installing data cabling, and there are electricians who don't have experience installing data cabling. So Brent's bringing up some important points about bend radius, termination procedures, and well, finally I'll vote for testing it to make sure that it passes the expectations. But you want to make sure the lengths are proper. You need to look at what components are installed to make sure that it is an industrial cable with a 600-volt rating with an oil resistant jacket, as opposed to an indoor rated cable that would have a simpler jacket design to it.
Okay, it looks like we have time here for just a couple more. This next one is, where can I find that file with all the test limits for each standard?
Oh, let me jump to that for just a second if my network would be so kind. On the Fluke Networks webpage, we have FlukeNetworks.com. On our webpage, in the support and downloads and updates, we're going to have that chart, and it's actually has been fairly popular. Here it is, the limit lines, and this has all of the different test limits that are available in the tester. So the TIA, the 568, the 1005, the ISO 11801 tests are all available from that document there.
Perfect. Okay, one more question here. Where would I use the zone enclosure that was shown? I believe, Mike Berg, this question is for you.
So the zone enclosure that we were showing, that's an access layer switch solution. So any of the cube style industrial DIN rail mounted switches will fit in that enclosure. It's a universal design. It builds in the structured cabling into the installation. So it has a patch panel in there. It also accommodates the fiber coming in. Where it comes up is when you're upgrading production lines and you do not want to disturb the existing control panel, or you don't have room to put the switch in with the control panels, a zone enclosure makes perfect sense. And that's actually the name correlates to, your cells, your zones on your manufacturing floor. Zone out where you're going to put that access layer switch. It will serve the different control panels and devices that are downstream from it, and maybe in that whole cell area, depending on how many nodes there are. So the application is at the level 0, level 1 access layer.
Okay, thank you, Mike. It looks like we are at the end of our questions here. If you do have any questions, please put it in the chat box or the question section of the GoToWebinar app. We'll give it just a few moments, guys, to see if any other questions come in.
No, we're good. We're good. Let's call it a day and go while we're ahead. Hey, thank you very much, everyone, for listening in. It's been good to have you here. Mike, thank you.
Yeah.
It's been a pleasure speaking with you. And Jane, great job running this. It's been very smooth.
Thank you so much, everyone, for
much.
hanging out with us for the entire hour and 15 minutes. So we really appreciate that.
Okay, it looks like we don't have any more questions coming in. On behalf of Panduit and Fluke Networks, I would like to thank everyone for their time today and their questions. This will conclude today's webinar.